Welcome to What Is, the show where we take the incredibly complex mysteries of the universe and break them down into something you can understand while eating a sandwich. Today, we're tackling a topic that is currently powering the device you're using to watch this. The lights in your room. And if you're particularly high-tech, maybe even your toothbrush. We're asking, what is electricity? Is it liquid? Is it magic? Is it just spicy air? Well, sort of. To understand electricity, we have to shrink ourselves down. Smaller, even smaller. Keep going until you're at the level of the atom. Everything in the universe is made of atoms. You, your dog, that sandwich I mentioned earlier, it's all atoms. And atoms are made of three tiny players: protons, neutrons, and electrons. The protons have a positive charge. The neutrons are just vibing, with no charge, and the electrons have a negative charge. Now, protons and neutrons are the homebodies of the atom. They stay in the center, the nucleus, living their best, stable lives. But electrons are the restless teenagers of the subatomic world. They orbit the outside, and in certain materials, which we call conductors, they are very easily bored. If you give them a little nudge, they'll hop from one atom to the next. That movement, that hopping, that's electricity. Electricity is literally just the flow of tiny, grumpy, negative particles looking for a better place to hang out. Now, you've probably experienced this on a small scale, when you rub your socks on a carpet and then touch a doorknob. That's static electricity. You've essentially kidnapped a bunch of electrons from the carpet, and they're sitting on your skin, waiting for a chance to escape. When you touch the metal knob, they all bolt at once. Zap, it's a tiny, personal lightning bolt. But for electricity to be useful, like keep the fridge running so the milk doesn't turn into cheese, we need it to flow constantly. This is what we call an electric current. To understand how a current works, engineers love using the water pipe analogy. It's a classic for a reason, mostly because it makes us feel smart. Imagine a pipe full of water. First, you have voltage. Think of voltage as the pressure. If you have a high-pressure pump pushing that water, you have high voltage. It's the oomph or the push behind the electrons. In the US, your wall outlet provides 120 volts of push. In Europe, it's 230 volts, which is why your American hairdryer will literally explode if you plug it in there without an adapter. Next, you have current measured in amps. This is how much water or how many electrons is actually flowing through the pipe per second. If voltage is the pressure, current is the volume of the flow. Finally, you have resistance, measured in ohms. This is the size of the pipe. A big fat pipe has low resistance. The water flows easily. A tiny, narrow straw has high resistance. It's harder to get things through. When you run electricity through something with high resistance, like the filament in an old light bulb or the coils in a toaster, the electrons struggle so hard to get through that they generate heat and light. This is basically the electrons getting frustrated and throwing a tantrum, which we then use to brown our bagels. So, we have electrons moving. But how do we get them to move where we want? We use a circuit. A circuit is just a loop. Electrons are very particular. They won't leave home unless they know they have a clear path back. If the loop is closed, they flow. If you flip a switch and break the circuit, the electrons just stop and wait. They're very literal-minded like that. Now, we can't talk about electricity without mentioning the two biggest nerds in history, Thomas Edison and Nikola Tesla. This was the original console war. Edison championed DC, or direct current. In DC, the electrons flow in one direction, like a one-way street. It's great for batteries, which is why your phone and your car use it. But DC is terrible at traveling long distances. You'd need a power plant on every street corner. Tesla, on the other hand, was all about AC, or alternating current. In AC, the electrons don't actually travel from the power plant to your house. Instead, they just wiggle back and forth 60 times a second, like they're at a very tiny rave. This wiggling sends energy down the line much more efficiently over hundreds of miles. Tesla won the war, which is why our power grid runs on AC. Edison was pretty salty about it, but he did give us the light bulb, so we'll call it a draw. So, how do we actually make these electrons start wiggling in the first place? Almost all electricity is created using a discovery made by Michael Faraday in 1831, magnetic induction. If you take a coil of wire and spin a magnet inside it, the moving magnetic field grabs the electrons in the wire and pushes them. That's it. That's the big secret. Whether it's a coal plant, a nuclear reactor, or a massive wind turbine. They are all just different ways to spin a giant wheel that spins a magnet inside a coil of wire. Solar panels are the only ones doing something different. They use the photoelectric effect, where bits of light, photons, basically punch electrons off of silicon plates. It's much more sophisticated, but, let's be honest, spinning a big wheel has worked for us for a long time. Electricity is the lifeblood of modern civilization. It's the reason you aren't currently reading this by candlelight while worrying about the plague. It's a fundamental force of nature that we've managed to trap inside copper wires and distract with gadgets. It's invisible, it's lightning fast, and if you touch it, it'll ruin your afternoon. But without it, the world would be a very dark, very quiet, and very boring place. Thanks for watching What Is? If you're feeling a spark of curiosity, make sure to hit that like button and subscribe. If you have a topic you want us to demystify, drop it in the comments below. Whether it's black holes or why your headphones always get tangled in your pocket, we've got you covered. See you next time, and keep asking, what is